so much for coming. I'm super excited to share all of the hard work that I put into this project. But before we talk about Skillfall, let's talk about you. It's a requirement. I'm not a narcissist. Anyways, hopefully you guys have seen me around. My name is May Chen. If you haven't, but I'm pretty involved at this school. As you can see here, I'm wearing my DECA pin. You guys should totally join DECA. There's Emira's right there. She's the best advisor ever. Anyways, I'm the social events director for DECA. And you might have participated in the trick-or-treat shoot that I hosted Halloween. We had over 20 clubs participate, and we trick-or-treating with the elementary school kiddos, so that was super fun. After this, I'm actually going to FBLA State, and I actually was district champion this year with my partner Oriana, that's in the crowd. And then last year we were also third at National, so you can see our banner up in the business hallway. I'm also the president of the National Chinese Honor Society, and I am the executive chair of the Colorado Gifted and Talented Student Board. Just this year, I was able to present for 7 professional organizations, including the Colorado Department of Education, the World Council for Gifted and Talented Students, and the Colorado Association of School Boards. And there I just advocate for using student voice and educational policy. And the most relevant part, that's enough about me, is that I am the class president for Chamber Orchestra. And so let me tell you a little bit about my violin journey. This is in 6th grade, very, very small. Anyways, I've been playing violin for 6 years. In no way have I ever been a prodigy. I believe that I worked really hard. I never took private lessons, basically just learned it from public education. So when I entered high school, I entered the beginner level of orchestra, concert orchestra. Here's me as first violin. Sadly, I'm no longer first violin. But then I moved up to symphonic sophomore year, and then junior year, I got into chamber. And I actually also played in the pit for the Little Women musical, and that's where I saw my most growth. And then this year, as the class president for Chamber Orchestra, I was so proud that 22 wolves got into the District Honor Orchestra. And basically the journey of getting 22 of us in there is what inspired this project. And so as you can see here, here are some scales. Do we have any musical or choir people in here? Anybody want to sing this for me? Yeah, that's wrong. So yeah, I could barely play with my fingers anyways. So as you can see here, these are super complex, but scales are super important in the audition process for anything because it just proves to the teachers or the judges that you'll be able to play the pieces in tune. And so as you can see here, it really translates. This is the excerpt I had to play to get into Little Women. It's super duper fast and they still expect you to play it in tune, but with practice you'll be able to do it. And so that brings me to my project, Skillfall. So what is Skillfall? Skillfall is a software system where a user can record themselves live playing a musical scale. If you guys didn't get what a musical scale is yet, if you know what Do Re Mi Fa Sol La Ti Do, that's what it is. And so basically, a user will be able to upload a live recording of them playing a 1-octave scale, and then it'll be able to return the % accuracy of it. And this whole entire thing uses Python sound processing libraries, physics, and music theory. And at the end, you guys get to enjoy a live demo of the app. So my objectives for this project was to first boost my portfolio. Since I am majoring in computer science next year, it's super important to have a marketable portfolio. And then I wanted to network with field professionals because it really just helps you get your foot out the door and into the professional world. So really important networking. And then I wanted to successfully complete independent research, wanted to graduate as a distinguished scholar, gotta get that nice cool. And then getting time management skills. So with my timeline, first I started with understanding scales mathematically because computers understand numbers and not music theory. So that was the first part that I had to learn. And then I had to learn the behaviors of how musical instruments, their sound waves, how they behave, because that is super important during the analysis process. Then I took a really long time on this Coursera for sound processing, which I'll get into later, but that was a bit of a setback. And then I began my back-end development in Python, and then I was able to implement an API so that I can move my front-end development into WinForms that uses C#. Now before we get into all of that research, let's talk about my logo. Super important in business, letting people know who you are right away. And so first, I'm analyzing musical scales. So of course, gotta have musical scales in there. And it's a sound processor, so I put a little cute robot on there. And then the model step by step, my advisor John actually helped me come up with it. Apparently it's from a K-pop song, but I really liked it because I thought it was encouraging since practicing scales is boring. And then finally I chose the color pink because it has this nurturing feel and it's approachable and this is a learning tool, so I thought pink was perfect. So now on to my advisors. Ms. Lowen is my orchestra teacher, but she also teaches AP Music Theory here at Grandview. And so she was really helpful in the beginning with giving me resources. Then Tomek, fun fact, she actually lives in Poland. And look at him on his cool motorcycle. Just Polish people, man. Anyways, so he's been super helpful. He's a software engineer for Customer.io, and he's actually the co-worker of my older brother. So that's one thing that's really cool about computer science is that you can work remotely but still work with people all over the world. And then there's Mr. Johnson. He is my AP Physics 1 teacher. He was really helpful with giving me reliable physics sources at the beginning. And then there's John Lim, as his title says, super smart junior. Anyway, we've been friends since like we were little. We did choir together and now we're in a relationship together. And he's super helpful. Ta-da! Look at all of these equations. I know we have Calc 3 in here. Can anybody tell me what any of this is? Okay. Anyways, it's fine because I didn't actually need to know all of these. I did learn them, but I only needed to know 5. Basically, I took this Coursera and it was entirely on sound processing, so not only was it analysis, but also synthesis. So I now know how to produce a sound just from math. I also know how to distort it or change the pitch, blah, blah, blah. But I didn't really need to know all that. So let's get into the actual relevant research. So first, let's start with the basics. Does anybody know what sound even is? You want to give it a try?
Sound is vibrations traveled over a distance.
So true. And it travels through particle-to-particle interaction, so it can be graphed in a sinusoidal function. Kind of like this. So then I decided to research the discrete Fourier transform, and it's super essential for any kind of sound analysis because it produces the spectrum of a signal. Basically, a spectrum of a signal is the projection of a signal onto a set of finite complex sine waves. Like here, I'm looking for the magnitude spectrum because then we'll be able to find the frequency. But I said complex sine waves. Does anybody know what that means? It means they use imaginary numbers. Calc 3 students, aren't you so excited? No? Anyways, so then, the one thing about the discrete Fourier transform is that it's actually a pretty demanding operation, so it makes my computer really slow. And my computer is already really bad. It doesn't have a lot of computer power. So good thing there are smart people in the world. We were talking about this with Ms. Rollins. She was saying, you know, some people, they did come up with these equations. And somebody came up with the fast Fourier transform. And basically, it takes advantage of symmetry. And by doing that, it decreases computational time. And that's super important because since I'm doing live audio processing, it needs to be able to keep up with the live samples. Then another thing, with my live situation, there's not really a concept of a whole signal. And the DFT can only be applied to a whole signal. So the short time Fourier transform is basically the DFT, but it's only applied to the most recent samples. And so now that I have produced this magnitude spectrum, it's important to window it so it can sum all of the segments into a bell-shaped curve with a maximum in it. More math, guys. As you can see, this maximum is called the spectral peak, and that's where you can identify the pitch and the frequency. And I decided to use the Hahn window because it shifts the signal and centers it around 0. And that just makes it easier for the computer to recognize where it is. And so now I was finally able to start coding. I began with a simple method and deriving this algorithm from equal temperament. So what this algorithm does, what this method does, it takes a note and then it is able to find its closest pitch. And how it does that is through equal temperament. So equal temperament is dividing up an octave into equal sections. And in Western music, we have a 12-tone equal temperament, which means each section has a ratio of 2 to the power of 112. So if we know a starting note, then we can find how many half steps or E, or 2 to the 112s are in between those two notes. And so we do know what the first note is. It's called the concert pitch. So if you guys have ever been to a symphony, the principal chair will stand up and play an A, and everybody will tune their instruments to it. That's exactly what a concert pitch does. And the most common concert pitch is 440 hertz, which is an A. And so here I had it return the note and within the pitch, so then I could confirm that it's actually returning an accurate result, because I know what an A sounds like, but I don't know what 440 hertz sounds like. And so then I began coding the function where I will be able to detect the spectral peak, but I also needed to access the microphone. And so here's just some code. I used the sound device Python sound processing library. And yeah, you just put in some stuff and then boom, the computer does it for you. Super nice. If you guys are interested in computer science, you should definitely pursue it. It's really satisfying. And so then after that, I was able to do all of my code, but then I ran into a setback, is that every time I ran my code, it crashed. That's the downside. But I realized it because since I was using the Haunting window, it can only accept one sample at a time, and I was giving it a whole entire list of signals. And so how I fixed this was every time a new signal came in, I removed the old one right away, so it's only analyzing the most recent samples. And then I was able to do a lot of stuff on there, as you can tell, but we don't have enough time to go into all of it. Honestly, it would be a lot. But in the end, I take this Haunting sample and then I multiply it by a certain step so that it becomes a harmonic product spectrum sample. And basically what it does is it multiplies it by a certain step, so only the fundamental frequency is left. And now I can return an accurate pitch. So now that all my back-end coding is finally done, and now I need to work on my front end. But I decided that I didn't want to have a user interface in Python because Python is really, really hard to make user interfaces in. And so I decided to use WinForms because it just has a drag and drop. It's not in here. It just has a drag and drop visual designer. So it takes out most of the coding for that. And since that's in C#, I don't have to learn 2 languages. I can only just focus on Python and then start doing my user interface and using the Visual Studio Driver. So here in Python, I first created an API so that I would be able to communicate with my WinForms app. And this is just telling it to start. And then after it starts, I have it analyzing the actual pitch, the list of the pitches that it recorded. So first I had to identify what scale it is. So I only had time to code for D major and C major, but these are the scales that every musician learns. Like these are the first ones that you have to learn. And then after that, it just compares those pitches to the actual pitches of what it should be and then returns the % accuracy. So simple math for those of you who aren't in calculus. And then finally, I just wanted to be able to check the data. So while I'm doing multiple runs, seeing what is going on, in case anything goes wrong, I can identify what it is. So here I have it returning like the actual notes that are played, the pitches that it says it's identifying, the individual % accuracy for each one of the pitches played, and then the overall. And so as you can see here, it's being displayed on my local server on my computer. And that's what it looked like before it gets sent to my WinForms, which is the user interface. So if you didn't get all of that, basically APIs help 2 computer applications talk with each other. And so then I started again doing my front-end research, which is just making things look pretty. You would think it would be nice, but actually I don't like front-end. It's really tedious, and sometimes it doesn't make as much sense as back-end. But anyways, here is the Visual Studio Tracker. It makes it super easy. All you have to do is drag it onto the WinForms, and then it already codes everything for you. So if you want to get into coding, like Microsoft apps, go ahead and use WinForms, and it's in C#. So I got the form controls on there. I got a label box, a combo box, and there's some 2 buttons. And and I connected them to my API so that when I started recording, a pop-up button would show up and say like, okay, we set the API, now it's recorded. And then here, when it stops, the API returns back the percent accuracy. And so then, after I got the form controls to start working, I began moving to making it look good. See, look, doesn't that look nice? So here, I added lots of images, started stop buttons, lots of docking and anchoring. And then here, you have a drop-down box. You can choose D major or C major. And I made it so that if you don't have scale selected, you can't click on a button, like the buttons are disabled, just so that the users, they are guaranteed to know that they can only play D major and C major, because if they played another scale, I'd be in trouble. And so once you select that, then you can click start, and then you can have either two outcomes. If you are above 100%, that means you played sharp, and if you're below 100%, that means you played flat. And so now, I would like to do a live demo. So John, can you please come on to it? Would you like to play D major or C major?
D major.
Yeah. Okay, I'll take it. Yay! Okay. My screen is really small, but it says 99.3% accuracy. He's actually first.
Go, John!
Yeah, let's hear for John. Alright, so that was super fun, but my overall goal in the beginning was to have this accessible to all the performing arts in this district so that people can really start to tune their ears. It's not about tuning their instrument, it's about being able to play in tune, and that's what brings a group of musicians to the next level. However, I can't necessarily do that right now because of the way that I first started learning. Since I was doing sound processing first, I started in Python, and then I just had to do all the recording in Python and doing all of the analysis in Python, and then just the UI just sent some APIs. But in reality, in the professional world, the user interface should be recording it, and then it'll send that recording to the API to get the back-end code to analyze it, then send that analysis back to the front end. And then that way everybody can download it and use it. But right now, because the back end is doing everything, you would have to download both the Python file and the WinForms file. Does anybody here know how to do that? So yeah, that's exactly my point. So hopefully, as I keep working on this, I'll be able to make it everything on the front end. And then also, I'm hoping to make the back end to be in the cloud so that it takes less storage when you guys do download it. So this is my bibliography. Are there any questions for me?
So you use a violin to show the live demo, but can you do it with other instruments or by singing as well?
Yes, you can. As long as it's one octave.
Do you have plans to add like multiple octaves later on, or
To add what?
like multiple octaves? Because you said you can only do it with one octave.
Yes, definitely. So when I first started, I wanted to do machine learning and actually be able to read like a one-time music sheet. But I definitely think that if I wanted to, I could move this into a machine learning project and let it be able to find that pattern. Because how I did this was I manually calculated what the actual frequency should be. But if I did do machine learning, it would definitely be easier to do multiple octaves.
Other questions?
Does the quality of the microphone affect your results?
I mean, my microphone is pretty bad, so I guess not. Like, you can come inspect my computer. It's like on its last time run. Yeah. Good.
Is this an application just for like a computer or can you get on your phone and tablet?
Yeah, so since I coded it in WinForms, it's only downloadable for Microsoft laptops or computers. But if I were to move it to like Android or Apple, I'd have to learn new languages.
How well does it work with the lower frequency instrument?
So I set it to the lowest E on the piano, but the reason why I don't want to go any lower is because then it can get into white noise and then that affects the analysis of it. So, but yeah, if you wanted to play it on the lowest keys on the piano, it would still work out.
So it's not a total range of only one octave, it's just that each scale that you play it can only be within one octave?
Yes.
Okay.
Does the final output take the average of all the outputs that you play throughout the piece?
Yes. So if I, let's go all the way back here, you see like each note accuracy. So these are the ones that they played compared to the one that it should actually be, and then it just averages all of that.
It seems like that maybe then it could spit out so you would know which note you were flat or sharp on, right? Like some instruments might care about that a little bit more. So, because it's just giving you an overall average, right? But could it also spit out?
Yeah, so I could totally add this as
Your
a
coding already has
function.
that in there, right?
Yeah, because this is like only available to me right now, but if I added that to the user interface, like they could totally see this.